Everybody, welcome. And today we have Samantha Scibelli from University of Arizona, Department of Astronomy. She's a graduate student. Working with Yancy Shirley, and she's also an SF graduate research fellow. And she's interested in star formation, astrochemistry, and especially radio astronomy. So here we go.
All right. Thank you for the introduction. Hi, everybody. Thanks for joining. Today, I will be giving a talk about the research that I've done here at the University of Arizona, looking at chemical complexity and the evolution of low-mass starless and prestellar cores. Before I get into the science, a lot of the research that I have done and a lot of the data I'll be talking about was collected with the 12-meter radio dish on Kitt Peak. And it's on Kitt Peak, which is a very sacred site to Tohono O'odham Nation. So I just want to take a moment to acknowledge that. Okay, so here's kind of the outline of what I'll be talking about. I'll be talking about a bunch of different kind of subtopics, projects. First, talk about chemical complexity and low mass star formation, why it's important to study this. Then I'll talk about a line survey that I did in one particular starless core that's very young, and why it's important to study complex organics in young cores. Then I'll talk about a survey that we did of a bunch of different cores, also with the radio telescope on Kitt Peak, then a high resolution dust study, which I'm working on now, and then some new results from a new survey that we're doing with the 12-meter, and then some exciting future research that I'll discuss at the end. Okay, so the type of objects that are in the title of my talk and that I'll be talking about for the remainder of the talk are starless and prestellar cores. So this typical picture is B68. It's a starless core. This visible image, when you look at it, you just see silhouette. It doesn't look like anything's there. This is a birthplace of low mass stars. It's very dense and cold. And so we use radio telescopes to probe this cold and dense matter. And you can see that that's not nothing there, that it's bright in molecular gas and dust. So these are images of the molecule 13CO that is present in this starless core. Now, there are a lot more molecules in space that we have discovered since CO. In fact, there are over 240 molecules that have been detected, most of them by radio telescopes. This is a table showing those. And the type of molecules that I'm particularly interested in looking for in these starless cores are called complex organic molecules. And some may say they're not complex, they are complex, but for the sake of this talk, I will define any complex organic molecule as those containing at least 6 or more atoms and at least 1 carbon atom. So highlighted in the table are those that I would consider complex, and marked in red are those that I've actually detected in the surveys I'll be talking about later on. So the reason why it's interesting to study these complex organics in starless and prestellar cores is because, this is a topic that astrobiologists, astrochemists are interested in trying to unearth, not necessarily, detections of life, right? These are the precursor molecules that are important for the building blocks of life, right? So these complex molecules, they're not signs of life, but they are important for making up simple sugars that will be important for DNA and RNA and things like that. So the question remains, are these molecules that are synthesized in space contribute to the chemical evolution for, emergence of life on Earth and things like that? And the best place, to kind of answer this question is in low mass star formation, because, you will eventually get a solar system type system where you can have potential life like our own solar system. And so this is the picture of low mass star formation, where you have a molecular cloud that condenses down in filaments, and there's these starless cores or prestellar cores, which are the dynamically evolved and gravitationally bound versions of those starless cores. And then you'll get a protostar forming where you'll have jets and outflows and accretion disks, and then a protoplanetary disk, which accretes matter and planets, believed to form in these gaps, and then eventually you'll get immature planetary system. So the question is, how are, these solar type stars evolve, and what kind of chemical inheritance gets passed on from preceding evolutionary stages? Because in all of these stages, complex organics have actually been found. So for example, there's a lot of work looking at these organics in comets, but also recently in Titan's atmosphere, this molecule vinyl cyanide has been mapped with ALMA, which is what this image here shows. And this vinyl cyanide is thought to be an important molecule for forming cell-like membranes, perhaps in liquid methane oceans, and important for like nitrogen-bearing life or something like that. Now in protoplanetary disks, there was this recent, you might have even seen it in the news. There was this discovery of the largest molecule to date in a protoplanetary disk, this dimethyl ether, and it was found even at this stage at very small scales. So we're even finding these complex organics in this protoplanetary disk stage. And then protostars have had a lot of complex organics detected towards them. This is an example of glycoaldehyde, which is a simple sugar for making things like RNA and DNA. But again, I am particularly interested in looking at starless and gravitationally bound prestellar cores because they are at one of the earliest phases in which these complex organics are observed, and they can give us better constraints on initial chemical conditions. And another motivating factor is that because these are, usually if you're looking at a protostar, these warmer regions where you have, internal radiation, the chemistry can be pretty well known. Things happen in gas phase chemical reactions because you have, material infalling and lots of stuff happening. But again, in these prestellar cores, which don't have internal radiation fields, it's still not completely understood how these molecules are forming at this really early stage. So not only are they a very early stage, but the chemistry that's happening in them is very interesting and not well understood. So it's important to study these large molecules in these very dense environments, but the question remains, how prevalent are they? And one of the roadblocks in kind of understanding this question is that up until some of my surveys, really only 4 cores, which I show here, have had complex organics detected towards them. For example, this L1544 is a very well-studied, very evolved core, kind of the poster child for a prestellar core. It has had a lot of studies done on it. But, what about for others cores or for younger cores, at what stage do we stop seeing complex organics? How early do we see them? These are all questions that I wanted to answer. So here I show a plot of abundance on the y-axis of different complex organics. For example, the green is that vinyl cyanide that I was talking about earlier, and they're all in respect to another complex organic, methanol. And in each colored region are different types of objects. So in this yellow region are dense starless cores, in the light blue region are protostars, and in this pink region are comets. And you can see that the abundances, follow each other. And L1544, that very dense core is here. It has complex organics detected towards it. These 3 other cores are a little less dense, but they all are very dense, well-known objects. So the question is, if we look even earlier into maybe not the prestellar stage, but the starless core stage, are we still seeing complex organics? So this leads to the first, or I guess technically second survey, but the first survey I'll be talking about in this talk. We decided to look at a particularly young core to really test the limit of see how early on we see this chemical complexity. So this core, not only is it much less dense than the other cores that were previously targeted, but it shows very low CO depletion, which, as a core condenses and gets denser, CO freezes out. And so you see a depletion of CO. And so that can give you an evolutionary, basically, tracer of your core. And you can see here in this plot, basically shows that the further down you go, the more depleted you are because it's a ratio of CO to the dense gas tracer N2H+. L1521E is an outlier where you have that very dense L1544 over here and another core here. So this core is believed to be very chemically young. So we wanted to target with the 12-meter radio dish on Kitt Peak and look for a bunch of different complex organics and see if we see anything. And we detected a lot of complex organics. So this is a table showing all the different molecules that we detect and all the different transitions of those molecules. You can see here, here's that dimethyl ether, the one that was detected in that protoplanetary disk. We're detecting it in this very, very early core. We also detect that vinyl cyanide, which was in that Titan's atmosphere and in other prestellar cores. We did try to search for glycoaldehyde, did not detect it, but we placed good upper limits on it. So this was exciting that we were able to actually detect complex organics in a very, very young core. And so now that we have, observations with our radio telescopes, we can turn those into abundances and do some more analysis. And one of the things that we can do is use our abundances from our line analysis to compare to chemical models. So this is a figure kind of showing the different ways in which you can form complex organics in cold cores. I'll focus on this desorption chemical model. It's basically this chemical reactive desorption. You have radical type molecules. You have molecules forming on the grains. Those get desorbed out, and then those radicals form in the gas phase to form more complex organics. And this is for specifically dimethyl ether I'm just focusing on here. There is a chemical model specifically for this type of reaction that has actually reproduced pretty well abundances. So that's what this y-axis is, abundance and time in years on the x-axis. Dimethyl ether is this pink line. And this model specifically, again, for that very evolved core L1544, it had reproduced abundances pretty well, also for other cores as well. But this was a model done specifically for the density and for the CO depletion factor that L1544 is in. But what about for L1521E? Can we also model with chemical models the abundances that we see? And the answer is no. So we use the same type of model that was done for L1544 and tried to reproduce abundances that we see in this very young L1521E. And again, this is a plot of abundance with respect to time in years. You can see, again, the pink is that dimethyl ether, and it very much underpredicts the abundances that we're seeing, which, this core is a lot less dense. It has a low degree of CO freeze out. So the model is not able to reproduce. For example, for dimethyl ether, it's not as dense, so you have more H instead of H2 floating around. So, your radicals such as C3O is destroyed more, and so you don't have your dimethyl ether and things like that. So there's things happening in the chemistry that is not producing high enough abundances. So this gas phase chemistry and reactive desorption alone is not sufficient to explain the observed complex organics in starless cores. So this presents a very unique and interesting challenge to chemical modelers out there. And so we need to do something else to explain the abundances that we're seeing at this very early stage. So here I'll show that plot again. We've now populated it with another starless core with some complex organics abundances on there, similar to some of these other cores. So that's great. However, there's still only 5 cores on this plot. Wouldn't it be great to have a more representative sample of cores? What if we looked at a bunch of different typical cores? Do we still see the same level of complexity? So this leads to the next project that we did, where we wanted to look at a more representative sample of cores. So this is the Taurus Molecular Cloud. It's the same cloud that L1521e is over here. And we decided to look at 31 cores along this filament here, which were already mapped in the dense gas tracer ammonia. So we knew, density and other things like kinetic temperature. So that's how we kind of decided to look at these specific cores. And we wanted to search for methanol and acetaldehyde, kind of one of the simplest complex organics, and then a step up in complexity to see how prevalent these molecules are in a more representative sample. And we found lots of complex organics. So methanol was detected in 100% of the cores targeted, and acetaldehyde was detected in 70%. So here are the lines here. Again, this was done with the Arizona 12 meter at roughly 3 millimeters or 96 gigahertz. These transitions are at. So one of the main results, or one of the things that we can do, is compare, again, get abundances out of our line analysis. And one of the things that we did was compare abundances, just comparing region to region. So the top plot is abundances of methanol versus core number. And each region is labeled less evolved or more evolved based on if there's protostars in that region. So if there's a protostar, we consider that region more evolved because there are objects in there that have reached kind of the next level of evolution. So you can see if you look in the more evolved regions, such as this red region here, you see lower methanol abundance. And in the less evolved regions, you see higher methanol abundance, suggesting that methanol is freezing out in these more evolved regions. And we can also look at this in another way, doing a virial analysis. So this plot shows, again, there's abundances on the y-axis. The larger plot is for methanol. The subplot is acetaldehyde. And this is the virial parameter on the x-axis here, which basically tells you, how likely is your core to be gravitationally bound the more towards this side of the plot you go. And you can see that abundances drop as the more evolved you get. Similarly for both methanol and acetaldehyde. So, could these molecules be chemically linked? It's not clear yet. But again, one of the results that we found from looking at this survey was, only a few of these cores are actually considered gravitationally bound. However, is that true? So we want to really know, are there most of these cores unbound by gravity? The way that these virial parameters were calculated were based on global measurements, based on the average volume density within which we were looking at our complex organics, which for the 12 meters, like a 60 arc second beam. And so one of the projects that I'm working on now is to really understand the evolutionary state that a subset of these cores are in. And so we wanted to get high resolution data for these cores in order to really nail down evolutionary states to then infer more about the chemistry actually happening. So this is a study that I'm working on right now that we are modeling cores in one particular region in this Taurus cloud. So this is the B10 region, one of those less evolved regions. There's 10 prestellar cores and filamentary structure in here that we can map at high resolution, which we've done. So here are the data. This is data taken with the IROM 30-meter dish in Spain and Granada. And we have high resolution 12 arc second 1 millimeter dust, and we have accompanying 2 millimeter dust that we got for free as well. So now that we have the high resolution dust data, the goal is then to get some physical properties out. So what I've been doing is doing some radiative transfer dust modeling, where basically you have a input of your telescope parameters, your location on the sky, and then you have parameters that you can vary such as opacity, interstellar radiation field, your profile of your core, how steep it is, the radius of it, the central density, which is a very important evolutionary parameter. And then RADAMC3D has an adaptive measure. It calculates column density, and it'll spit out continuum maps that we can then compare directly with the data that we've taken, both the 1 millimeter and 2 millimeter data, but I also have corresponding Herschel data as well that we can add in to get better constraints. So this is what I'm working on now. Currently, we have a grid that runs through different central densities, the density exponent, which tells you how steep your profile is, and then we have two-dimensional X and Y parameters, and then we also can vary the opacity law, or we can scale the interstellar radiation field as well to decide
I found this on the web.
What we're looking at.
Reacted to your, sorry.
So this is what we have so far. We're still working on adding to the grid, but basically what we'll end up doing is we'll have one of the diagnostics that we'll have will be to look at the radial profiles of our grids. So here is an example. This plot shows 4 different sectors of one particular core. This is core 9. In the contours in the bottom of the panels, it shows you which section of the core we're getting a radial profile from. And so you can sector off and kind of see which model, given the best central density, radius, opacity, fits the data. So this is, again, the intensity versus radius. So different radial profiles for different cores, and you have best fits for each individual. And then we also have best fits for all of the different sectors. And so we'll have a range of best fit models that can be used to then go back into our Virial analysis, and we'll be able to better understand the evolutionary parameters for these cores. So stay tuned for more on this. We're still running things on the HPC here in Arizona, and we'll have some exciting results from that soon. So even though we still, don't have the exact evolutionary stages of these cores yet, we have increased the sample size of complex organics in prestellar cores. There's now 20 of these cores that we have acetaldehyde and methanol detected towards that we can add to this plot and increase our sample size. And we continue to see high abundances and abundances that are within a factor of 2, I would say, across evolutionary stages, suggesting that there is possible chemical evolution between different stages of star formation. But this leads again to another question that I had. Only 2 of these cores are outside of the Taurus Molecular Cloud. So I wanted to know, is this, does this trend occur in different environments? What if we look outside of Taurus? So this leads to another survey that I'm doing and currently ongoing, again with the Arizona 12-meter dish, but also we have time this summer with another telescope in Spain, the EBS 40-meter dish, that will look at a subset of these cores in greater detail for even more complex organics. But for now, we're just looking again at methanol and acetaldehyde for now. And in the Perseus Molecular Cloud, those objects that are labeled in pink have already been observed. There's a few in blue that have yet to be observed, the similar for the Aquila Molecular Cloud. And already we have detected methanol in 100% of the cores. And then we also searched for acetaldehyde in Perseus. We have a detection rate of 38% and Aquila 30%. Now, if you remember when I talked about Taurus, the detection rate for acetaldehyde was higher at 70%, but you also have to consider that these clouds are at different distances. Taurus is a lot closer to us, so 135 parsecs. Perseus, where we're looking on average is 300, and then this Aquila rift, this region, right, in Serpents, this Aquila region is like 700 or 470 parsecs away. So if we were to have, put Taurus at the distance of these clouds, given a, typical source size of our cores that we're looking at, I calculated, what do we expect the detection rates to actually be? For Taurus at a Perseus distance, it would be around 19%, and for Aquila, it would be at 0%. So actually, given their distances, I would say that it's still very prevalent in these distant clouds, these complex organics. The fact that we're detecting them at 30%, even in the samples that we have so far. So all of this to say, complex organics are forming early and often, also in different clouds. And so I'm still working on getting exact abundances out for these, but stay tuned for more on this survey. Okay, so lastly, before I wrap up, I do want to talk about this future work, which I'm very excited about. This is a survey called Glucose, the GBT L1544 Unbiased Complex Organic Survey. This past semester, we proposed for time with special project time at the GBT, which is a 100-meter dish in West Virginia. And this is a legacy program, so we have over 600 hours of time, which has been accepted over 3 years. While we will observe many complex organics and other molecules within one particular core, this evolved core L1544, which I had mentioned before. And this core is, because it's very evolved and very well studied, and has a good, density, temperature profile that people have really studied very well. The lines will be brightest, and we have a good model to then compare our line analysis to, and to get good, to get a good understanding of the chemistry that's actually happening. So we expect there to be a lot of complex organics within this particular range, which is one of the motivations. So we're looking at about 38 gigahertz to 48 gigahertz. And it turns out that complex organics in this region are predicted to be a lot brighter even than the range that I've been looking at with the 12 meter, which is at like 96 gigahertz or something. So this is kind of the motivation why we want to look in this particular region of the spectrum and do an unbiased search to kind of get all these complex organics, but also to see if we see things that are, that we weren't expecting. So this is synthetic spectra, basically predicting how bright we think we're going to see some lines in this band. So even though this has just basically started in March or something like that, we already have 7% observed, so 2 subbands along this frequency spectrum, and we have some preliminary data already, which is very exciting. And if you zoom in, we are detecting complex organics, so it's exciting. This is acetaldehyde and vinyl cyanide that we see here. So stay tuned for more on the complex organic side. Another really interesting and cool piece will be that, not only the complex organics, but there's going to be other bright lines at really high spectral resolution, because GBT has one of the a very high spectral resolution here. It's 0.01 kilometer per second. And so there'll be very bright lines in this survey that other people can then use for, studies of kinematics or isotope ratio, things like that. So it'll be great for the public to also use when we do release the data. Okay, so thank you all for listening, and I'll just run through kind of the summary. We had this survey that looked at complex organics such as acetaldehyde, dimethyl ether, methylformate, and vinyl cyanide in a chemically young core, L1521E. The paper's there if you want to check it out. And we find that, some complex organics are seeded very early on in the star formation process. We have this survey of 31 cores looking at methanol and acetaldehyde, which you can find in this paper. I'm currently working on 3D radiative transfer models of a subset of cores in the Taurus region, which will get good constraints on evolutionary parameters, which will tell us about conditions needed for complex organic molecule chemistry to thrive. And there's ongoing surveys, in particular, the one of cores in the Perseus and Aquila molecular clouds, which will do abundance trends for different environments. So thank you very much, everybody, for listening, and I'd be happy to take any questions that you might have.
Okay, so question from here first. Okay, sure.
Yeah.
It's a nice talk. I just wonder, you have any age constraints for the B2 11 to 13 filament?
Oh, yeah.
Or was there any other constraint for the time scale of that filament?
Let me see. The B213, which is the red region?
Yeah, or this the B230, B211, just that long film. Like you have an age constraint on that from the either the chemical model or do we know the age of this?
Yeah, I'm not sure. That's a good question. Yeah, we haven't looked at the exact ages. It's hard to tell based on their like abundances. The chemical age kind of is scattered because of the, for all of these cores. So it was hard to tell exactly. But I will say that this, this B213, we did map methanol all in these different subregions, and there was a lot more methanol in this particular region, B211 and B10, than there was in B213. And again, there's a lot more protostellar activity in B213, which is an indication that it's a little bit more evolved, but I'm not sure exact timescales yet. Yeah, thanks.
Me, another question from Vladimir from Zoom.
Yes, hello. Thanks for a great talk. I just have a question about the physical sizes of those regions. So what's your angular resolution of those observed regions of the high concentration of those molecules? The second related question is that you mentioned N2H+, but do you also have that data on HCO+? Because the ratio of HCO+ to N2H+ gives you information about the ionization degree of those regions, and which probably provides clue about the formation of molecules, because these molecules are probably ionization driven sources, right? So it's not only X-ray, probably it's also particles. If it is the case, then you need to have some kind of signatures of shocks. So what's your any comments on those questions?
Yeah, so the angular resolution for our for the methanol and acetaldehyde, the beam is like 60-ish arc seconds, 1,000 or 2 AU scales. And so, yeah, when we did map, it's not at exactly high resolution because you have, arc second scales. In terms of HCO+, I think there must be some HCO+ data, but I'm not actually sure. But there is, C18O and some SO observations of this filament. But yeah, HCO+ a mapping or a targeted search at particular cores would provide some good insight on ionization. Yeah.
Yeah, so the data, I think that ALMA observed HCO+. So if you can find data, ALMA data from at least some of the sources, that will be interesting to look at.
Yeah, yeah. Unfortunately, things like ALMA have been difficult in this region because it is so close, so things get resolved out pretty quickly, especially they're not as dense as, say, that L1544 source that I was talking about. But yeah, I think L1544 has HCO plus definitely mapped towards it. And there have been studies done talking about, you know, how these molecules form. A lot of recent studies on cosmic ray driven chemistry has been done, which suggests that can also really help drive the formation of these complex organics, which I didn't talk about specifically in this talk, but it's definitely something that should be added to the chemical models to definitely consider, because there are cosmic rays and they are driving the chemistry.
Thank you.
Thanks.
Okay, any other question? Now, I have one question.
Yeah.
Is there a similar study? I mean, I've started survey done for Orion. Like there'll be more kind of distance will be closer to Aquila, probably. Yeah. A little bit further away, but still you can compare them. And I'm particularly interested because the environment, UV radiation environment is different.
Right.
And whether chemically they would look more evolved or not.
Yeah, that's a good question. We haven't looked at Orion because, again, the distances, but the fact that we were like, let's see if we see anything in Aquila. And then I realized how far away Aquila was. And I was like, whoa. Right. So, yeah, I mean, we could look at Orion. Yeah, I mean, it is such a different region because of the O and B star and the UV radiation. So it would be interesting. I know that people have looked at protostars in that region and find lots of complex organics. Yeah, like HH1 or so, like some of them on the plot that I was showing here, Orion here. Yeah, there's a few protostars that have had really good maps. And there's a lot more coming with ALMA in those regions, but yeah, I'm not sure if anyone has looked in the Prestellar course, but that would be also interesting to look at.
Okay, another question. All right, so then let's thank Samantha again. Then actually there is a special emergency talk tomorrow, so hopefully we'll see you tomorrow. Thank you for coming.
Thanks, everyone.